Hello, everybody, and welcome to week 10 of Math 1220 online. Just a few quick announcements. Your exam one grades have been posted. Most of you probably already saw that from the Canvas announcement, but if you didn't see that Canvas announcement, go ahead and check out your grade, and also look at that Canvas announcement. It was posted on March 3rd, and that has some more details about your grade. Good, and then speaking of exams, it's already time to start thinking about exam 2. That's coming up in week 12, which is March 27th to 31st. The scheduling and resources are available now on Canvas. So for example, if you scroll down on the main Canvas page for this class, you'll see in week 12, here's exam 2, and you have the exam 2 information and resources you can click on to see the practice exam, the formula sheet for exam 2, and so on. Okay, great. So you have that available. And do read this announcement if you haven't already. Okay, so this week in 1220, we're doing convergence tests for series. So that's sections 9.3 to 9.5. And again, so basically the idea here is in most cases, it's actually hard to compute an exact value for an infinite series. So instead of sort of trying to compute whether here's like the exact value for this infinite series, mostly what we're concerned with is just whether it converges or not. So whether it converges or diverges. So because we can't compute the exact value, because we can't give like a precise formula for it, usually the way we have to decide whether it converges or diverges is by comparing it to either an improper integral or a really simple series, like a geometric series, where we can just compute it explicitly to decide whether it converges or diverges. So you'll see a lot of this week. Let me just quickly go over two illustrative examples. So say we're trying to compute the sum from n equals 1 to infinity of 1 over n squared. You can find a precise formula for this, but this is actually a famously difficult problem. It's challenged mathematicians for many years before it was finally resolved. It's called the Basel problem, if you're interested, BASEL. So that's sort of the problem of giving a precise formula for this. But okay, so what's much easier though is just to understand whether it converges or diverges. And one way we can do this is by noting that like this sum from n equals 1 to infinity, well, it sort of looks like a Riemann sum. So one of these like estimating sums we use to define integrals. So if we look at the integral from 1 to the infinity, so it's improper integral from 1 to infinity of 1 over x squared dx, so computing sort of the area under this purple curve, then this blue sum, the sum from n equals 1 to infinity 1 over n squared, it sort of looks like this Riemann sum where we approximate the area under this curve by sort of looking at this box, then this box, then this box, then this box, then this box, and so on, all the way out. And so it's not such a bad idea to think that probably this sum sort of that approximates this integral will converge exactly when this integral converges. And that's really the case, and that's an example of the integral test. So if you evaluate this, you'll see that this integral does converge, and from that we'll be able to deduce that this sum converges. You'll be able to compute exactly what value this integral converges to, but the value that this integral converges to won't tell you the value this sum converges to. Because after all, if you look at this, like this picture tells you like this sum is not equal to this integral. I'm just hoping that sort of they behave approximately the same way. So like if one will be infinite if and only if the other is infinite, for example. So it's not enough to compute this sum, but it's enough to tell whether it converges, to look at whether this integral converges. So that's something called the integral test. And so there we'll put to use all this study of improper integrals we did earlier. So that's one type of example. Another type of example is just sort of comparing infinite series that sort of look sort of complicated to a simple infinite series. So here we might look at the series the sum of n times 1/2 to the n. And so the idea here is if we didn't have this n here, if we just had the 1/2 to the n, so that sum from n equals 1 to infinity 1/2 to the n, like this is just a geometric series, and we would know that it converged and even what it converges to from the stuff we did earlier. And well, but somehow you should think like this series, like it isn't so far off from this series. And somehow the idea is that 1/2 to the n, like that gets small, sort of much quicker than sort of n gets big. So somehow like this is the thing that dominates the behavior of this series. And to make that precise, what we can really say is like if we look at the ratio of two successive terms, it's like the nth term to the n plus first term, well, the ratio of those two terms is n over n plus 1. Sorry, it's n plus 1 over n. Fix that. N plus 1 over n times a half. Well, so this sort of like I am increasing a little bit, like I'm not sort of multiplying by a half at each step, like this series. Like I'm sort of getting a little bit bigger than that. But so like the factor I'm multiplying over is n plus 1 over n times a half. And this n plus 1 over n, like if n is really big, then n plus 1 over n is sort of basically 1. So and somehow, even though this doesn't behave exactly like a geometric series with ratio 1/2, somehow like for n really big, it does sort of look like I'm sort of basically growing by a half at each step. And because of this, I can really deduce that this series converges basically for the same reason that the geometric series with ratio 1/2 converges. So this is an example of something called the ratio test. And somehow the idea of it is that you're comparing an arbitrary series to a geometric series. Okay. And so basically you're going to be developing tools like this based on comparison or other ideas that will tell you, that will sort of let you tell whether a series converges or diverges. And that's sort of what you're focused on this week. Well, enjoy it, and I'll look forward to seeing you in office hours or hearing from you via email. And have a nice week. And I hope you also are having or have a nice spring break. Bye.